So good afternoon, everybody. So today, basically, we are starting the second phase of our orientation and slicing studies, where we'll be discussing about the deposition orientation studies in rapid prototyping. So again, this will be a series of algorithms and works done by different researchers, based on which we actually gain some knowledge and insight how the deposition orientation actually works in the softwares. So what is the importance of orientation? Now, why do we give so much preference to orientation? Because orientation plays a very significant role during the part fabrication stage. So the main thing is that, like, if you have got a cylinder like this, now you want to fabricate the cylinder. So what you need to do is you need to orient the cylinder in a particular way so that it basically helps you to get the fabrication done. Now when you go for slicing, now before you go for slicing, you actually need to put this onto the part bed. This is your bed. So how are you going to keep this on the bed in order to, as you already know, build time, surface finish, and shrinkage, or mechanical properties. You can also call it as mechanical properties. So all these things need to be understood before you start to go for orientation. So a part deposition orientation can definitely improve a surface quality. It can definitely reduce build time. It can definitely increase the dimensional accuracy, because dimensional accuracy, when I talk of dimensional accuracy, I'm talking about the shrinkage effects, Okay. When I'm talking about surface quality, I am talking about two things: surface finish as well as aesthetics. Aesthetics is the visual output of the body. So there are a lot of issues which are involved over here. Now if you can control all these points, you can definitely reduce the cost of the prototype, and the number of support structures or the volume of support structure will also actually reduce your cost of the prototype as well as your time also. Now this thing also can be reflected in build time also. Like suppose you are making an inverted part like this, so if you are making it in this direction, so this is your z axis. Suppose if you are making it in this direction, so this is an overhanging part, so this section is overhanging. So in order to prevent any toppling, because what will happen is this will topple, क्योंकि जैसे जैसे उसका क्रॉस सेक्शन ऊपर की तरफ जाएगा, उसकी मोमेंट ऑफ इनर्शिया शिफ्ट होने लगेगा, क्योंकि इस बॉडी का मोमेंट ऑफ इनर्शिया कहीं यहाँ पर होगा, यहाँ पर कहीं होगा. तो जैसे जैसे ये मोमेंट ये दूर जाएगा, ये इसके टॉपलिंग होने के चांसेस बने रहेंगे. So in order to prevent any toppling, you need to create support structure. This is called as support. So how much support is needed, whether the support is needed or at all, whether it is needed at all, that is also a very valid question. So orientation plays a very significant role in all these studies. Now if I make this same part like this, then I don't need a support structure. ठीक है ना? My geometrical tolerance will also be better, because over here the thin section is transferring into thick section. Over here thick is going to convert into thin, so shrinkage will be less over here as compared to in this section. So all these things combined together play a very important role in defining the orientation of the object. Now, as I just asked you, nobody answered that question for me. Suppose you have a cylinder like this. Now you have sliced this cylinder. Now there are two possible orientations. Now if I just plot the platform, so this is your x-axis, this is your y-axis, and this is going to be your z-axis. Now one possible orientation is this, and the second possible orientation is this. Now if I slice this like this, that is not going to work. So what I need to do is I need to slice it in cross section. So the moment I slice this into cross section, what will happen is you will start to experience the staircasing effects. Staircasing effects basically lead to surface roughness. ठीक है? So when surface roughness increases, the orientation is not correct. If surface roughness is going to increase, the orientation is not correct. So defining the orientation of a body with respect to the part is something that you need to understand all these points to be very precise. You need to understand all these points. Now, if you ask somebody whether you work on all these 4 points simultaneously, again, that is not possible. I have already explained this in the previous class that surface quality and build time are not going to be controlled simultaneously. Now, if you are trying to control surface quality, then the layer thickness is going to be less. The layer thickness is going to be less. And when layer thickness is less, build time is going to be high. On the contrary, on the opposite side, if you are looking for dimensional accuracy, again, the layer thickness has to be less. So the build time is always going to be higher. So as I said, there are different orientations and different aspects. But before you decide on the orientation and the layering process, you need to understand why the part is being manufactured. Is the part being manufactured for proper strength? Is the part being manufactured for aesthetics? Or is the part being manufactured for demonstration only? Based on your application of that part, you need to decide what will be your orientation and what will be your layering. Now, this is your nozzle head, and your nozzle head, basically this is your nozzle head. If I call this as your nozzle head, now this nozzle head is going to move in XY direction. This nozzle head is only going to move in XY direction, and the Z axis is going to be utilized using this machine bed. The Z axis is going to be controlled by this machine head, and this is going to move by 1 layer thickness. This machine bed is going to move by 1 layer thickness. And what will the nozzle head do? It will basically contour your contour, 2-dimensional. So now there are a lot of effects that you need to consider. A circle is being plotted on a 2D contour by the nozzle head, whereas this thickness is going to be controlled by the movement of the machine bed. So in order to control the dimensional accuracy, what you need to understand is that once the layer has been deposited, whatever heat has been dissipated on the platform has to be balanced before your next layer is plotted on the previous layer, which means again the machine bed has to move by 1 layer thickness up or down. So depending on the heat that is going to be input, so the new constraint that comes is the nozzle temperatures. So there are a lot of issues which are going to come up either simultaneously or concurrently, means one at a time. So all these issues actually play a very significant role in deciding what should be the orientation of the part. So once you have dimensional accuracy, or you have finish as your criteria, don't bother about your layer thickness, because the layer thickness is going to be on the lesser side. And the orientation, now let me come back to orientation. Now the orientation has to be such that the contact area with the machine bed, has to be minimum. Because what happens is the bottommost layer that is in contact with the table gets deformed out. The bottommost layer which is in contact with the table generally gets deformed out. As a result, what you will observe is something of a deformity. When you start working with the process, so you need to understand that the bottommost layer is going to get deformed, and in order to control that deformation, what you need to think about is that the contact between the layer and the surface has to be minimum. Now, this is not always going to be true also. This is always not going to be true. So in some circumstances where we cannot compromise, in that case, what we do is, suppose if I'm making this cylinder, let us assume this cylinder is of 50 mm height. This cylinder is of 50 mm height. So what I will do is, I will make this cylinder of 55 mm. I will make the cylinder of 55 mm, and the bottom 5 mm, I will simply cut out, so that the bottom surface becomes smooth. So post-processing is definitely needed in order to control or in order to minimize the effect of orientation. So when you have a orientation and a bottom layer getting deformed, one solution is that you increase the height of the component and go for post-processing in order to get the uniform object. So as I said, in almost all the cases, you have to be very careful with respect to orientation. Now, as I explained this example, you might have understood by now. Now, if this is my part, the green is my part, and that has been layered. So whether this overhang is so significant that the object will topple out, you have to decide on this. You have to decide. A layer thickness has been defined. Now, if you think that this overhang is not very significant to cause toppling, so when will the toppling happen? Anybody? When will the toppling happen? The toppling will actually happen when the moment of center is outside the body. So over here, it will not be outside, it will be inside. But on the contrary, if I have a figure like this, then in that case it will be outside. So there is a very good chance it might topple out. So whether you need support or not, that has to be decided by you beforehand when you see the object. Okay, so you have a minimum area of contact as compared to this is the maximum area that could be in contact. You have taken the minimum area of contact. Now, before you start fabricating, you decide whether this needs support or not. So orientation is added with support decisions also. Now, on this side, now if you want dimensional accuracy, or in other terms, what we call is that as a form accuracy, that whatever form we wanted to create has to be created. Now, this is one possible orientation with minimum contact area, because this length is more, this height h is more than L, h is more than L. So you have taken the minimum contact area, but what you observe is that there is a critical feature. Now, if this critical feature is actually sliced, there is a very good chance this feature might miss out. So this is not the right orientation. So the right orientation would be something like this. So you cannot balance out the minimum area and the critical feature criteria. So now you have taken the maximum contact area in support. So what is recommended is that if this is h dash h, then h plus 2 mm will actually help you to get the accurate part. So all these decisions have to be made during the process while you are doing the pre-processing of the CAD model, while you are working with the CAD model. So as you might have known by now, so you do tessellation. Now, once you do tessellation, now you have to put the part on the platform. You have to put the part on the platform. So how to put the part on the platform? What should be the layer thickness? This is the criteria that we are discussing about. So support structure generation again is something which is very critical to be decided at this stage itself, whether you want the support structure or whether you don't want the support structure. And if any product has features, then how to save that feature from getting ruined out. So one of the first works that was done was basically done by Frank and Fadel in 1994. And what they did was they developed a expert system based on selection of direction for build mainly for stereolithography process. So they took three basic criteria. The decision criteria were surface finish, build time, and support structure. But there was a hierarchy. All these criteria were taken one at a time. You cannot define a function which will have three boundary conditions in one equation. So first you had to give a weightage. Like if you have three criteria, 1, 2, and 3, so you had to decide which is your primary criteria. As I've always explained to you, if you are showing it for if you are using it for assembly, then surface finish becomes your primary criteria, support structure becomes your secondary criteria, so this becomes 1, this becomes 2, and build time becomes your third criteria. So based on that, you decide your criteria. Now, as I said, it is taken one at a time. So surface finish has to be oriented in such a way that a feature on the critical surface is eliminated. That any critical surface, if it has a feature, that feature will not be taken into consideration. What you have to think about is minimum cusp height. What you have to think about is minimum cusp height. So surface finish is related to minimum cusp height. Now, when you talk of build time, the build time is basically related to slicing. So the rough estimation of build time is done using the number of slices and time taken for each slice to be fabricated. The time taken for each slice to be fabricated. Now, support structure was based on the area that would be needing support. Suppose if I'm making an inverted L section, so I have to find out this cross section that will be needing the support. Based on this cross section, I will decide whether the support is needed or support is not needed. There is no mathematical background for deciding on any of these criteria basically. So what person needs to do is he needs to decide on how to put 1, 2, and 3, that is surface finish, build time, and support structure, like surface finish, build time, and support structure as their decision criteria. So they framed a set of rules. So what were the rules? If the feature axis of two surfaces of a revolution are parallel, orient the axes in Z direction. These are the feature axes of a triangle, of a cylinder, sorry. These are the feature axes of a cylinder. Now, if the feature axes are exactly parallel to each other, because to draw a cylinder, you need to create a circle, and then you need to extrude this circle and create a circle at the top. So these are two feature surfaces, this circle and this circle, which will define a cylinder. Similarly, for a cube. So what he said is that if you have two surfaces of revolution which are parallel to each other, then orient the axis in Z direction, which means the part is to be fabricated in Z axis. So this is going to be your Z axis. So you have to cut this like this. The orientation has to be across Z axis. Don't bother about build time. Don't bother about support structure, because that will automatically be minimized if you are making the part in Z axis. Secondly, if the feature axis of a hole and a freeform surface are perpendicular. Now, suppose you have a simple cube. I'm not taking a complicated surface. I'm going to explain this through simple surfaces, and it has a through hole, a genus to be very precise. Now, if this has a through hole, don't orient it in this pattern. Don't orient it in this pattern. Rather, the orientation of the feature axis is not well understood. So this feature should be generally fabricated in Z axis. This feature should generally be fabricated in z-axis, which means the center of axis of the circle and the center of axis of the cube, since they will be coinciding, hence they should be fabricated in z-axis. Then another thing what he told was that if there is an inclined plane, and there is a surface which are perpendicular to each other, then it is always recommended that all the fabrication should happen in the z-axis. Don't bother about the cross-sectional surface area. Don't bother about the cross-sectional surface area. All the feature axes should move in the z-axis. All the feature axes should move in the z-axis. And the orientation of the feature axis should be perpendicular to the z-axis. It should be perpendicular to the z-axis. So there are some objects which need to be manufactured in this orientation, and some objects which need to be oriented across xy plane, and some orientations which need to be across z-axis. So it all actually, these rules, these are not what you can call as that hard and fast rules. These are more like suggestive rules, because you will not get a simple surface in a CAD model unless you are making a simple primitive like a cube or a cylinder or a wedge. You will get simple surfaces over there. But if you are making a freeform surface, like if you are trying to create the body of a car, so if you are trying to create the body of a car, what will happen? You will get lots of freeform surfaces. So when you talk of freeform surfaces, the orientation of the freeform surfaces is going to be at an inclined plane. So always you have to focus that when you are trying to orient this part, you have to orient in such a way that the finish or the build time, one of these two basic criteria are minimized. Generally, support structure in this theory is an add-on which automatically gets modified, or rather minimized. I would rather use the word minimized, because whichever process you take, if you take build time, support structure will always get minimized, because when you are reducing the build time, the support structure would automatically minimize, because you are going for adaptive slicing. Similarly, if you are going for surface finish is minimized. That means the layer thickness will be reduced and the support structure will automatically not be needed, because you will not be having thicker slices. Okay, so in this way, support structure automatically gets adjusted. So the basic criteria that you can think of is build time and surface finish. Which of these two are basically going to be minimized? Based on Frank and Fadel's work, Chang came up with a new function. Now, Chang came up with new functions. Now, if you see Frank and Fadel, he had 3 decision criteria, but all the 3 criteria were independent. What Chang did, he made 2 criteria, that is accuracy of the part and build time, and one was a primary function and one was a secondary function. So part accuracy he determined as the primary of function, and build time as the secondary function. So here you don't need to make any choices. Your accuracy of the part is your primary function and build time is your secondary function. Now what he decided was that build time is actually estimated by the height of the part. Definitely. So suppose if you have a part like this, so if you are cutting in this axis, that is you are slicing this part as an XY axis and this is your Z axis. So if this part with minimum support structure is kept and it is sliced in Z axis, you have many slices. Okay, but XY contour is less. And similarly for the same part, now if you orient it like this and slice it over here, what you see is less slices. Now this is your Z axis, so less slices, but what happens to your XY contour? It increases. So number of slices actually directly affect the height of the part. The number of slices directly affect the height of the part, because when you talk of build time, the contouring motion also takes a lot of time. If you have to make a small circle and if you have to make a large circle, definitely the time to contour also comes under build time. It also comes under build time. So what this Chang said was that build time is basically dependent on the height of the part in the deposition direction. So if this is the deposition direction that we have considered, so this is the deposition direction that we had considered. So number of slices more, build time will be more. Number of slices less, build time will be less. But again, here he is not considering the time to contour the individual layer. He is not considering the time to contour. So what happens is that the minimization of build time actually is dependent upon not only number of slices that you generate, it is also dependent on the time taken to contour each and every layer. Now suppose if you have a sphere, and you cut that in z-axis, what you will see, there will be a smaller circle. The next layer there will be a larger circle, next layer there will be an even larger circle. So each layer will have different time to contour. Okay, so when different times to contour come into picture, that overall time to fabricate the part, or the build time that we call it, is going to vary, and it is going to increase depending upon the layer thickness. So if you have a smaller layer thickness, you will have larger number of slices, more contouring is needed. If you have thicker slices, less contouring is needed, so you will have smaller build time. So what he did was he defined the surfaces that were available and gave them a weighing factors. So he defined lot of surfaces. So there is an up-facing horizontal surface based on the surface normal that you have already learned. So every freeform surface was thought to be a combination of various plane surfaces, and their weights were calculated. Now these weights that you see over here, these are not standard weights. These are user defined. So based on Chang, he started finding out the suitable orientation based on first of all observing on the part what are the number of surfaces that the part has. So he had 14 criteria for surfaces. So let's assume on a CAD model, he had number 3, he had number 2, then he had number 5, and then let's say he had number 10. So these are the 5 surfaces that were available. So now if I see the weightage for each of the criteria, I have the weightage factors. So what I now do is I simply add those weightage factors. So if the weightage factor for this is 4 plus zeta 2j plus zeta 3j. So this is the weightage, and zeta functions were calculated using computational geometry of the CAD model. So all these functions can be actually taken out as an numerical quantity. So once you rotate that part, now this is for one orientation. Now you check for another orientation. Now when you went for another orientation, actually what you found was 2 went out, 5 went out, and rather you had 6 and 8. So now you again measure the functions. Okay, weights. Suppose you checked for 5 orientations, and you had 5 functions. Now you had 5 functions. So 5 weight functions you got. Out of those 5 weight functions, which weight function had the least value? So the least weight value is taken as the best accuracy for the solid model. So the complete surface is divided into segments. Each segment is assigned a weight, and you add that weight to get out the best accuracy for the function. Now, both the processes that I've just explained to you are very complex functions, and these complex functions are very difficult to determine for somebody who doesn't recognize surfaces properly. For a common person, for a person who has not studied CAD, identifying a surface becomes very difficult. So LAN in 1997 came up with a very simplistic function and a very simplistic model. So what was this model all about? The first decision criteria is surface quality. So what you do is you check for maximum parallel and maximum perpendicular surface area. Is it a functionally important surface or an aesthetically important surface? And which is the area which can be minimized according to the worst surface class. Now, what is the worst surface class? I have already showed you one example from the joint that whatever surface is getting degraded is the worst surface. So in any CAD model, when you are fabricating, there is a surface that you can always compromise. There is always a surface that you can compromise. So identifying that worst surface is very important. The second criteria is build time, and the third criteria is support. So the whole concept of quality and build time actually LAN computed with respect to the support structure. So if you identify the support structure, you can minimize the build time and you can increase the surface quality. So how did he do it? First of all, he formulated a point which needs support if it is the endpoint of a supportless edge, if the length of overhang is more than the critical value, or if it is the geometric center of a supportless plane. Now, let me give you an example. We have an inverted L plane. Now, what you need to find out is where is the geometric center of this body? Where is the geometric center of this body? Now, if the geometric center of this body lies outside the model, if it lies outside the model, you need support. If it lies inside the model, you don't need support. So that is the first criteria. Okay. Now, if it lies outside, suppose if there is a part like this, I'll just give you a 2D image so that you understand it better. Now, if I is over here, you don't need support. If I is over here, then you need to check the support. Now, in order to check the support, this is the amount of overhang. This is the amount of overhang. Now, what is the length of this overhang? What is the length of this overhang? Now, this value has to be found out. Now, once you find out this value, now again you check whether this I lies inside or outside this critical value. The amount of overhang by 2. The amount of overhang by 2, you find out that value. You have found out that value, you draw a perpendicular line, and then you check for this value of I. If I or the instantaneous center lies within or with outside, if it lies within, again the overhang is more, but plane is horizontal. The plane is horizontal, no support needed. No support needed because it will not topple. If it lies outside this, if suppose point I moves over here from, if this point I actually lied over here, then in that case, it will definitely topple. It will definitely topple and you need support. So what happened was the number of points which needed the support were minimized. So when you minimize the support structure, what happens is your build time automatically is going to decrease because support structure generation is going to reduce. And as a result, your build time is definitely going to decrease. Same way, when the build time decreases, the surface which is going to be in contact. Now, suppose this surface doesn't require support. So in that case, this surface is not going to degrade. बिकॉज सपोर्ट स्ट्रक्चर जहां भी लगेगा वहां जब हटाएंगे सपोर्ट स्ट्रक्चर को तो वहां डिग्रेडेशन होगा सरफेस पे. आपने एग्जांपल के साथ अभी देखा है. सो if no support is needed, just quality will automatically become better. So the whole idea over here in this theory is not the surface quality, not the build time, but rather how to reduce the support structure. So when you reduce the support structure, automatically your build time and your surface quality will improve. your build time and your surface quality will improve.